Within a span of just 72 hours, two stars detonated with such ferocity that they became visible to the naked eye. A pair of magnitude 6 earthquakes ripped through Venezuela, and a massive solar eruption struck the only confirmed interstellar comet currently traversing our skies. Scientists dubbed this window the 72-hour stack. But no one anticipated that everything would converge simultaneously, including 3I/Atlas itself, which took a direct hit from a coronal mass ejection CME. The probability of this cosmic and seismic collision occurring together is less than 1 in 1,000. Is this merely a freak convergence, or are we overlooking a deeper pattern? A cascade of rare, high-energy phenomena, all compressed into 3 days, demands our attention. If you're wondering just how improbable this really is, let's examine the numbers. On average, the world witnesses perhaps one naked-eye nova per year, sometimes none at all. This time, two exploded into view within a day and a half of each other, both brilliant enough for backyard stargazers to spot without even a telescope. In Venezuela, the region typically experiences a magnitude 6 earthquake once every 2 or 3 years. Yet two major quakes, plus a powerful aftershock, struck the same zone in less than 6 hours. Meanwhile, the sun, already turbulent at the peak of its activity cycle, hurled a coronal mass ejection directly along the orbital path of an interstellar comet, a target so rare that it's only the third one ever confirmed. When you stack up the numbers, the probability of all these events landing within a single 72-hour window plummets below 1 in 1,000, possibly far lower, depending on the mathematical approach you use. Statisticians call this phenomenon Poisson clustering. Sometimes randomness deals a hand, so extraordinary it seems rigged. The odds of witnessing a pair of naked-eye novae within 3 days, less than 0.002%. Two Venezuelan earthquakes of that magnitude occurring back-to-back, approximately 1 in 10,000. Add in a CME brushing past 3I/Atlas precisely as it enters the inner solar system, and you're venturing into territory where calculators essentially surrender. This is why even veteran researchers are calling it an event stack. It's not merely the rarity of each individual occurrence. It's the way they overlap, making the entire window feel almost impossible. The phrase itself is already circulating in astronomy and geophysics circles as shorthand for a week when a universe appeared to discard its rulebook. The numbers are unambiguous. This is a statistical outlier of the highest order. That's what makes it so difficult to ignore and so compelling to map out minute by minute, to see just how tightly these odds-defying events truly fit together. The clock begins ticking just after midnight Universal Time. At 2:12 a.m. Universal Time Coordinated on September 23rd, the first nova, V1935 Centauri, flashes into detectability. Survey telescopes in Chile and South Africa capture the outburst within minutes, with automated alerts logged and public confirmation following in less than an hour. Local time in Centaurus, it's still the depths of night, but the news is already spreading through international networks by dawn in Europe. Fast forward to late evening on September 24th, 22:21 Universal Time Coordinated. To be precise, seismographs across the Caribbean register a sharp, shallow rupture, a magnitude 6.2 earthquake near Yaguaraparo, Venezuela. The epicenter sits at a depth of approximately 7.8 kilometers. Local clocks read 6:21 p.m., just as residents are finishing dinner. Within minutes, preliminary reports hit the Venezuelan seismic network's feeds, with the USGS and EMSC echoing the event in their global catalogs. Less than 6 hours later, at 3:51 Universal Time Coordinated on September 25th, the ground convulses again, this time at a magnitude 6.3, slightly deeper at 14 kilometers, but in the same region. The area is jolted awake once more. Aftershocks, including one registering approximately magnitude 5.8, ripple through the zone in the following hour. Hospital logs and WhatsApp message chains timestamp the chaos in real time as medical staff scramble to respond. Just 14 minutes after the second quake, at 4:05 Universal Time Coordinated, another astronomical alert is triggered. V7994 Sagittarii erupts into visibility, its peak brightness reaching magnitude 6.2. Automated pipelines push the discovery to public feeds, and multi-wavelength sensors detect both gamma-ray and X-ray signatures. Amateur astronomers begin comparing notes with professionals, their excitement palpable despite the late hour. Meanwhile, in the background, the sun is building toward a critical moment. Over the course of September 25th, a coronal mass ejection launched the previous day's sweeps through the inner solar system. Models place its arrival at the projected path of 3I/Atlas within an 8-hour window. Estimates center on midday UTC, but the precise overlap depends on the latest ephemeris and solar wind velocity. Alerts from the Space Weather Prediction Center go out within minutes of each new reading as scientists and comet watchers track the plasma front's progress. Each timestamp is anchored to universal time, but every event leaves its own local footprint. Chile's telescopes operating in the pre-dawn chill, Venezuela's hospitals functioning under evening blackouts, and solar physicists watching data streams update in real time. The stack of events, minute by minute, forms a timeline as dense as any in recent memory, each marker a pin in the map of an extraordinary 72-hour window. A nova is far more than a sudden brightening. It's an eruption on a white dwarf, a stellar corpse that quietly siphons hydrogen from its companion star until the accumulated fuel sparks runaway fusion. Within a matter of hours, the system's light can surge by a factor of 100,000, temporarily outshining a billion suns. That's precisely what happened before dawn on September 23rd, when V1935 Centauri, a faint star in Centaurus, leapt to magnitude 5.8, just within reach of the naked eye from a dark field, a rarity even for seasoned astronomers. Gabriela Moya, an amateur astronomer in Valparaiso, Chile, was the first to confirm the outburst. She spent the night running remote telescope sessions, scanning for anything unusual. Despite clouds and power cuts, she persisted, driven by both the thrill and the burden of being first. Rumors of a nova flickered through Discord channels, but Moya waited for certainty. When her report reached the Central Bureau for Astronomical Telegrams at 2:12 Universal Time Coordinated, she had barely slept in 2 days. Her alert triggered a wave of automated confirmations across the Southern Hemisphere, and soon the nova's coordinates were flashing through global networks. The spectacle of a nova lies in its physics. Hydrogen from the companion star accumulates on the white dwarf surface, compressed by gravity until temperatures soar past 10 million degrees Celsius. Fusion ignites in a runaway chain reaction, blasting the outer layers into space at thousands of kilometers per second. The explosion creates a shockwave that tears through the ejected gas, hitting it until it glows in visible light, and even more brilliantly in gamma rays and X-rays. With V1935 Centauri, orbiting detectors picked up clear gamma-ray and hard X-ray signatures as the optical brightness peaked. That's the fingerprint of powerful shocks, evidence that the blast was accelerating particles to near light speed and possibly forming dust grains in the aftermath. Less than 2 days later, another white dwarf in Sagittarius, V7994 Sagittarii, followed suit, reaching magnitude 6.2, just on the edge of unaided visibility. The discovery sparked debate as multiple survey teams raced to claim the first detection, their reports bouncing between telescope logs and social media. High-energy satellites like Fermi and Swift caught the event almost instantly, recording a rapid spike in gamma and hard X-ray bands. Internal debates at NASA and among the Fermi team delayed public release as data was checked for false triggers. When the detections were finally announced, preprints poured in, each probing the shock physics and particle acceleration behind the outburst. What links these novae is the violence of their shock signatures, visible in both the light curves and high-energy emissions. These are not gentle brightenings, but thermonuclear runaways unfolding in binary systems light years away, yet brilliant enough to etch their story across our sky. The first quake struck just after sunset near Yaguaraparo, a magnitude 6.2 at a depth of 7.8 kilometers. That's shallow enough for the rupture to race straight to the surface, shaking homes and sending power lines swaying. The local hospital, already short on supplies, scrambled to set up triage outside as aftershocks rolled in. Senior nurse Maricela Rivas, who had just ended her shift, found herself back in the thick of it, guiding patients onto color-coded tarps spread across the parking lot. Her voice, steady over the hospital's WhatsApp group, relayed injuries and urgent needs as volunteers rigged up makeshift water stations and moved the most critical cases away from cracked walls. 5 hours later, the ground moved again, this time a magnitude 6.3, deeper at 14 kilometers, but centered almost directly beneath the same region. The sequence followed a classic stress transfer pattern, one fault segment slipping, then loading the next. University of Los Andes seismologists, working through the night, mapped the rupture's progression along the Acumer-Ancon fault zone. Their analysis pointed to typical aftershock decay known as Amori's Law, the biggest shocks up front, then a trailing series of smaller tremors. Within an hour, a magnitude 5.8 aftershock rattled the area, forcing patients and staff to evacuate the building again. Hospital cooks, pressed into service as spotters, watched the walls for fresh cracks and called out when it was safe to return. The immediate aftermath was defined by improvisation. With only 3 operating tables and intermittent power, Rivas and her team prioritized children and the most severe trauma cases. They rotated patients outdoors as aftershocks hit, using flashlights to guide 4 lines and monitor vitals. Local radio stations relayed updates from the hospital, broadcasting lists of needed supplies and safe routes for ambulances. In those hours, the hospital became a nerve center, not just for medical care, but for information and community coordination. Seismologists reviewing the event cluster emphasized that despite the timing, the quakes followed well-understood geological patterns. The crust in this part of Venezuela is under constant strain from the slow grind of the Caribbean and South American plates. When one segment slips, the stress redistributes, sometimes triggering another rupture nearby. Each aftershock was a reminder that in a week when the universe seemed to be rewriting the odds, the earth beneath their feet still played by its own rules. Solar maximum isn't just a buzzword this year. It's a daily reality. Sunspot numbers have surged to 165, and the solar radio flux is holding above 180. That's the kind of environment where coronal mass ejections become almost routine, with the sun tossing out dense clouds of plasma every few days. But what's different now is what's sharing the inner solar system with those storms. 3I/Atlas, only the third confirmed interstellar object. 3I/Atlas isn't following the usual script. Its orbit is strongly retrograde, nearly skimming the ecliptic plane, and it's moving at over 60 kilometers per second, much faster than typical comets. This trajectory brings it within 0.19 astronomical units of Mars on October 3rd, a close flyby that has Mars orbiter teams on alert for possible imaging and spectroscopy opportunities. Most comets we study originate from the Oort cloud or Kuiper belt. 3I/Atlas comes from another star system altogether, carrying materials and volatiles that predate our sun. Its timing couldn't be more fortuitous. Passing through the solar system right at the peak of solar cycle 25, it's exposed to the most energetic and variable solar wind conditions we've seen in over a decade. That makes it a natural plasma probe, an object whose comb and tail can reveal in real time how interstellar material responds to intense solar weather. Dr. Stephen Burns, a geophysicist known for his work on solar-terrestrial interactions, has called this passage a once-in-a-generation experiment. He points out that while we've observed CME impacts on solar system comets before, we've never had the chance to watch it happen to an interstellar visitor. The closed Mars flyby adds another layer of intrigue as planetary scientists scramble to coordinate observations from orbiters like TGEO and MAVEN. Every data point gathered now could help decode both the comet's origins and the physics of plasma interactions at solar maximum. So as 3I/Atlas sweeps past Mars and heads for perihelion on October 29th, it's not just a curiosity, it's a rare, moving target for heliophysics and planetary science alike. The sun's heightened activity, the comet's unique path, and the timing of his encounter turn a routine solar storm into a scientific opportunity that won't come again soon. October is stacking up to be a month for the record books, and there are several windows where sky watchers and citizen scientists can get directly involved. The next headline date is October 20th and 21st, when Comet Swan, designated C/2025 R2, makes its closest approach to Earth at just 0.26 astronomical units away. That's about 39 million kilometers. With the new moon and the Orionids meteor shower peaking at the same time, Conditions couldn't be more favorable for catching the comet's faint tail. For the best view, head out after midnight, far from city lights, and give your eyes at least half an hour to adjust. Binoculars in the 7x50 or 10x50 range will help, and a star chart or phone app can guide you to Swan's position as it glides to the pre-dawn sky. On October 29th, 3I/Atlas reaches perihelion, its closest point to the sun in this passage, about 1.36 astronomical units out. While it won't be visible in broad daylight, experienced observers may attempt twilight or dawn viewings, but only with extreme caution. Never look anywhere near the sun without ISO 12312 to 2 certified solar filters, and never use binoculars or telescopes unless the filter is securely attached over the front lens. Even a brief unfiltered glance can cause permanent eye damage. For comet and nova hunting, patience pays off. Dark adaptation is key, and red flashlights or dim screens help protect night vision. The third major date is December 19th, when 3I/Atlas makes its closest approach to Earth, about 1.8 astronomical units away. This is when the comet is most accessible for amateur imaging and visual observation, especially if its activity ramps up after perihelion. Citizen science platforms like the AVSO, American Association of Variable Star Observers, International Comet Quarterly, and the Comet Observation Database are already posting calls for magnitude estimates, tail sketches, and time-lapse photos. If you capture something unusual, a sudden brightening, a tail kink, or a suspected disconnection event, log the time, location, and equipment used, and compare notes with others before posting to official channels. Responsible reporting helps filter genuine discovery from noise and keeps the data useful for researchers. For those organizing group sky watches, especially with children, review safety basics before dusk. No direct solar viewing, keep all optics pointed well away from the sun, and post reminders about certified filters and safe laser use. The excitement of these events can tempt shortcuts, but a moment's caution protects both eyesight and scientific credibility. As October and December unfold, the sky is offering a rare invitation, one that's best answered with clear eyes, careful methods, and a healthy respect for both wonder and safety. In just 72 hours between September 23rd and 25th, 2025, 2 naked-eye novae, twin magnitude 6 earthquakes in Venezuela, and a coronal mass ejection intersecting 3I/Atlas all occurred. The documented probability of this event stack is less than 0.1%. As new data arrives from upcoming milestones, the Mars flyby, Swan's approach, and perihelion, community observations and careful analysis will separate coincidence from connection. The record stands. Sometimes nature's rarest patterns play out in plain sight, challenging our understanding of probability and reminding us that the universe still has the power to surprise even the most seasoned observers. Whether the 72-hour stack represents pure chance or hints at deeper connections we don't yet understand, it serves as a powerful reminder that we live in a dynamic, interconnected cosmos where the extraordinary can unfold before our very eyes. The next time you look up at the night sky, remember that you're witnessing an ongoing experiment, one where the universe occasionally deals a hand so improbable that it demands our attention, our curiosity, and our best scientific efforts to understand what we're truly seeing. Dr. Elena Voss had been staring at the same data for 3 days straight. As director of the Multi-Messenger Astrophysics Lab at Caltech, she'd seen her share of cosmic coincidences, but this felt different. It started with a graduate student's offhand observation during the October 20th Skywatch. While dozens of observers trained their telescopes on Comet Swan, Sarachin noticed something odd in the archived gravitational wave data from LIGO. There was a whisper, not a detection, but a pattern of microfluctuations spanning September 23rd through 25th. Too faint to trigger alerts, but rhythmic, persistent. It's probably nothing, Chin had said, uploading the filtered signal to the shared drive at 2:47 a.m. Maybe truck traffic near the detectors. But Voss couldn't shake it. She cross-referenced the gravitational data with the nova timings, the earthquake sequence, even the solar wind measurements from Parker Solar Probe. At first, nothing. Then she shifted her approach. Instead of looking for causation, she looked for resonance. The numbers aligned with eerie precision. By November 8th, the scientific community was watching 3I/Atlas with renewed intensity. Post-perihelion observations revealed something unexpected. The comet's coma was pulsing, not the usual outgassing fluctuations, but a regular 11.3-hour cycle that matched no known cometary behavior. Dr. Stephen Burns, coordinating observations from Kitt Peak, was the first to publish preliminary findings. "We're seeing coherent oscillations in both the sodium and cyanogen emission lines," he wrote in an astronomer's telegram at 1934 Universal Time Coordinated. "The frequency suggests external forcing, not internal sublimation dynamics." Within hours, 3 independent teams in Japan, Chile, and South Africa confirmed the pattern. The oscillations had begun on September 25th, the same day the second Venezuelan earthquake struck and V 7994 Sagittarii erupted. That's when Voss made the connection that would change everything. Late on November 12th, Voss convened an emergency video call with a small group of colleagues: Burns, Chun, seismologist Dr. Marcus Reed from UCLA, and Dr. Yuki Tanaka from JAXA. She shared her screen, displaying a complex frequency analysis spanning electromagnetic, seismic, and gravitational datasets. "Look at the fundamental frequency," Voss said, highlighting a spike at 0.024 Hz. "It appears in the LIGO noise floor on September 23rd. It's embedded in the P-wave arrivals from both Venezuelan earthquakes, and it's modulating the gamma-ray light curves from both novae." Reed leaned closer to his camera. That's not possible. Seismic waves don't couple to astrophysical phenomena across interstellar distances. Unless they're all responding to the same underlying perturbation, Tanaka interjected. "A space-time ripple we can't directly detect yet, but that's strong enough to trigger instabilities in systems already near critical thresholds." The room fell silent. What they were discussing bordered on speculative physics, the kind of idea that could destroy careers if proven wrong. "There's more," Voss continued, pulling up 3i/Atlas data. "The comet's oscillation frequency, 0.024 Hz. The same signature. It arrived from outside the solar system, already carrying this pattern." Chin spoke up, her voice tight. "You're suggesting 3i/Atlas isn't just any interstellar object. It's a marker, a probe, maybe, or a natural resonator responding to something we're not equipped to measure directly." "I'm suggesting," Voss said carefully, "that the 72-hour stack wasn't a coincidence. It was a convergence, multiple systems, spanning geological and astrophysical scales, all responding to the same stimulus. And that stimulus might be ongoing." As 3i/Atlas made its closest approach to Earth on December 19th, observatories worldwide turned their instruments toward the comet. What they captured sent shockwaves through the scientific community. At 4:17 Universal Time Coordinated, the Hubble Space Telescope recorded a brief, intense burst of polarized light from the comet's nucleus, lasting exactly 41.7 seconds, the reciprocal of 0.024 Hz. Ground-based observers using interferometry detected a corresponding spike in magnetic field strength. And in a development that defied all expectations, 3 separate gravitational wave detectors recorded simultaneous, coherent signals. This time, the pattern was unmistakable. LIGO Hanford, LIGO Livingston, and Virgo all showed the same 0.024 Hz oscillation, amplified 1,000-fold above the September readings. The signal lasted 9 minutes before fading below the noise floor. Dr. Rainer Weiss, Nobel laureate and LIGO pioneer, was pulled from retirement to review the data. His response, delivered to a hastily assembled press conference on December 21st, was measured but profound. "We have detected what appears to be a gravitational wave carrier signal, extremely low frequency, possibly originating from beyond our galaxy. The September events may have been precursors. Harmonic resonances triggered as this wave passed through our local cosmic neighborhood." He paused, choosing his next words carefully. "If confirmed, this suggests that what we witnessed wasn't random clustering at all. It was synchronization. Multiple systems, white dwarf binary stars, tectonic fault zones, solar plasma dynamics, and interstellar comet, all briefly entrained to the same deep rhythm in space-time itself." In the weeks following the December detection, Voss's team worked around the clock to model the implications. If a gravitational wave could trigger such diverse phenomena simultaneously, It suggested a new understanding of how cosmic events cascade across scales. But it also raised an unsettling question. Late on Christmas Eve, Voss and Burns stood outside Kitt Peak's main dome, watching 3i/Atlas fade into the winter constellations as it began its long journey back to interstellar space. "The comet's pulsations have stopped," Burns said quietly. "The frequency signature is gone." Voss nodded. "Whatever was broadcasting stopped after the December signal. Or we passed through it. Do you think it was natural?" Burns asked. "Some kind of astrophysical phenomenon we've never encountered?" Voss was silent for a long moment, watching the comet's faint tail stretch against the stars. "I think," she said finally, "that 3i/Atlas came from somewhere that wave originated. And I think it responded to something it recognized." She turned to face him. "The real question isn't whether the 72-hour stack was coincidence or connection. It's whether that signal was saying hello, or just letting us know something is listening." Above them, the universe turned in its ancient silence, keeping its secrets as it always had. But now, for the first time, humanity had heard something whisper back to the fabric of reality itself. And deep in the archives of gravitational wave observatories worldwide, automated systems continued their vigil, listening, always listening, for the next time that impossible frequency might return. On April 3rd, 2026, 3 novae erupted within a 48-hour window across different constellations. Simultaneously, a magnitude 6.1 earthquake struck Indonesia, and the Sun unleashed a coronal mass ejection that intersected the path of Comet 67P/Churyumov-Gerasimenko. This time, the gravitational wave detectors were ready. They recorded the pattern immediately, 0.024 hertz, clear and unmistakable. Dr. Voss, now leading a global consortium called the Temporal Convergence Initiative, issued a statement that made headlines worldwide. "We are beginning to understand that the universe operates on timescales and to mechanisms we're only now learning to perceive. The 72-hour stack was not an isolated incident. It was our first lesson. The cosmos, it seemed, had more to teach. And humanity was finally learning how to listen." By June 2026, Dr. Elena Voss's Temporal Convergence Initiative had grown from 5 researchers to an international collaboration spanning 43 institutions. What began as a hunt for gravitational wave correlations had evolved into something far more ambitious, mapping the hidden periodicities that seemed to govern cosmic events across all scales. The breakthrough came from an unexpected source. Dr. Amara Okonkwo, a complexity theorist from Lagos who specialized in emergent systems, joined the team in May. While others focused on the physics of gravitational waves and seismic coupling, Okonkwo approached the problem from a different angle entirely. "You're all looking for causation," she said during a June 15 video conference, her screen filled with network diagrams. "But what if this isn't about one thing causing another? What if it's about synchronization, like fireflies flashing in unison or heart cells beating together?" She shared her analysis, a topological map of every detected 0.024 Hz event since September 2024. Instead of plotting them chronologically or spatially, she'd arranged them by their phase relationships, how the peaks and troughs of each oscillation align with one another. The pattern that emerged was stunning. "It's a network," Okonkwo explained. "Each event, novae, earthquakes, solar flares, cometary outgassing, acts as a node. They're not connected by force or energy transfer in any conventional sense. They're connected by timing, by resonance." Dr. Marcus Reed, the seismologist, leaned forward. "You're saying the Earth's crust is somehow phase-locked to stellar explosions light years away?" "Not directly," Okonkwo replied, "but they're both responding to the same underlying metric perturbation. Think of it like this. If space-time itself is oscillating at 0.024 Hz, any system that's poised at critical threshold, a fault line under stress, a white dwarf approaching nova, a comet's coming near sublimation pressure, will tend to slip at the moment when that oscillation reaches maximum amplitude." Voss felt her pulse quicken. "So the gravitational wave isn't causing these events. It's conducting them." "Exactly. And here's what makes it remarkable." Okonkwo pulled up a new visualization, a three-dimensional web of connections pulsing with light. The network is strengthening. Each convergence event adds more nodes. It's like the universe is waking up. The next major test came sooner than anyone expected. On August 11, 2026, the Parker Solar Probe detected unusual oscillations in the solar magnetic field during its 21st perihelion pass. The frequency, 0.024 Hz, but this time accompanied by harmonics at integer multiples, 0.048 Hz, 0.072 Hz, 0.096 Hz. It's scaling up, Dr. Stefan Burns reported from his new position at ESO headquarters in Germany. The sun isn't just responding anymore. It's amplifying. Within 18 hours, the predictions began coming true with unsettling accuracy. Okonkwo's network model had forecast 4 high-probability nodes. But this time, there was something new. Dr. Yuki Tanaka was the first to notice it. While analyzing the August gravitational wave data, she applied a technique normally reserved for pulsar timing arrays, looking not at the wave itself, but at the subtle variations in its phase and amplitude. There's structure here, she announced during an emergency session on August 15th. The 0.024 Hz carrier is modulated. It's carrying information. The room erupted in crosstalk. Voss raised her hand for quiet. Show us. Tanaka displayed her analysis, a spectrogram revealing narrowband features nested within the main signal. They weren't random fluctuations. They showed regularity, patterns that repeated across the 9-minute transmission. I've extracted what I think is the embedded signal, Tanaka continued. It's a sequence of phase shifts. Binary, essentially, high phase versus low phase, repeating in groups. Sarah Chun, now a postdoc at MIT, spoke up via video link. How many groups? 72, Tanaka said quietly. The silence was profound. It could be coincidence, Reed offered, but his voice lacked conviction. At what point, Burns said slowly, do we stop calling these things coincidences? Voss made a decision. Yuki, can you decode it? Treat it as if it were intentional. See if there's a coherent message in those phase groups. I've already started, Tanaka admitted. It's going to take time. The sequence is complex. News of the August convergence leaked on August 18th through a graduate student's unguarded tweet. Within 24 hours, the story had gone viral. The Temporal Convergence Initiative found itself thrust into the global spotlight. The public reaction was mixed. Some hailed it as humanity's first contact with an intelligent cosmos. Others dismissed it as pattern-seeking and noise. Religious communities divided sharply. Some seeing divine communication, others warning of cosmic deception. The scientific establishment was more cautious. A editorial in Nature on August 21st captured the prevailing mood. While the correlations documented by Voss et al. Are statistically compelling, the leap to attributing meaning or intelligence to gravitational wave modulations requires extraordinary evidence. The TCI team has provided intriguing data, but not yet proof. Voss understood the skepticism. She felt it herself in quiet moments, but the numbers kept mounting. By early September, the network map showed 247 confirmed nodes, events spanning seismic, astrophysical, and solar phenomena, all phase-locked to the 0.024 Hz fundamental. The probability of such synchronization occurring by chance was vanishingly small. More importantly, the pattern was accelerating. As the second anniversary of the original 72-hour stack approached, Okonkwo's model made a startling prediction. A major convergence event would occur on September 23, 2026, beginning at approximately 1830 Universal Time Coordinated. The network topology suggests this will be the strongest synchronization yet. Okonkwo explained during a September 20th briefing. We could see 10 or more simultaneous nodes activating. If the pattern holds, we should also receive another gravitational wave burst, possibly longer and more information-rich than before. The world watched. Observatories from pole to pole prepared their instruments. LIGO Virgo and CAGRA coordinated observation windows. Seismologists placed additional monitors along predictive fault lines. Amateur astronomers crowded online forums, sharing telescope feeds and speculation. Dr. Voss found herself giving interviews to outlets from CNN to the BBC, carefully threading the needle between scientific rigor and public curiosity. "We're witnessing something unprecedented," she told a panel on September 22nd. "Whether it's a natural phenomenon we've never encountered or something more directed remains to be seen, but the universe is speaking. We need to listen carefully." That night, unable to sleep, she walked through Caltech's campus under the pre-dawn sky. In 3 days, this would all culminate, either in confirmation that would revolutionize humanity's understanding of the cosmos, or in disappointment that would mark her as the leader of science's most elaborate case of collective apophenia. Her phone buzzed. A message from Tanaka. "Found something in the phase data. Need to show you. It's not random." Voss's hands trembled slightly as she typed a reply. "I'm on my way." The universe, it seemed, wasn't done with its revelations.